The Big Bang is a concept that has influenced our comprehension of the universe, laying the groundwork for modern cosmology. Based on Einstein's theory and the accepted Standard Model, the Big Bang was the moment when the cosmos began its expansion, marking the creation of all matter, energy, space, and time. This occurrence, approximately 13.8 billion years ago, led to the vast universe we can observe today. However, recent advances in cosmology suggest that there may not have been a single absolute origin. Instead, there might have been a phase before the Big Bang that was equally important in forming the universe as it currently exists. This period, also known as cosmic inflation, is one of the most captivating features of modern cosmology. It proposes that, before the hot and dense state of the Big Bang, the universe went through a remarkable, rapid, exponential expansion. During this period, the size of the universe increased at an astounding speed. To illustrate the extremity of this expansion, if the universe began smaller than an atom, it would have expanded to be far larger than the entire observable universe within a fraction of a second, about a millionth of a second. Though brief, this stage of growth played a crucial role in shaping the universe. When inflation concluded, the energy driving the expansion of space was transferred into heating the universe and forming the particles of matter that make up everything we see. In many ways, inflation is the forerunner to what we currently call the Big Bang. While the theory of inflation is widely accepted in cosmology today, many questions remain unanswered. We still do not fully understand what caused inflation to begin, what caused it to end, or how long it lasted. These are some of the most pressing unanswered questions in cosmology, and solving them is crucial for a deeper understanding of the universe's origins. Before inflation, the universe existed as an incredibly dense, tiny point of matter, frequently referred to as a singularity. Expansion began from this point and eventually led to the creation of atoms, molecules, stars, and galaxies. Although the Big Bang is a compelling origin story, modern cosmology points to a more intricate picture. Some theories suggest that the universe went through a time before inflation. After the Big Bang, the universe's expansion was triggered, doubling in size exponentially at least 80 times in an instant. This rapid growth was powered by a mysterious form of energy that permeated empty space. When inflation ended, this energy was converted into heat, producing particles and creating the hot, dense state we refer to as the Big Bang. The inflationary stage was icy and empty, but it established the foundation for the creation of matter and the universe we observe today. One of the more speculative theories in modern cosmology is the idea of eternal inflation. This theory suggests that inflation didn't stop everywhere at the same time. Instead, it ended in different regions, creating numerous distinct zones, or bubbles, each of which could be a universe in its own right. According to eternal inflation, our universe is just one of these patches. There could be an infinite number of universes, each with its own physical constants and laws. This is where the idea of the multiverse enters. Our universe may be just one of many, or even an uncountable number. If this theory is correct, it might explain why life is perfectly suited to our universe. In a multiverse scenario, universes could exist with all possible combinations of physical laws. We simply happen to live in one where the conditions are ideal for stars to form and for elements like carbon and oxygen to exist, elements necessary for life. Despite theories like eternal inflation and the multiverse remaining speculative, the idea of inflation itself is supported by actual evidence. The strongest evidence comes from the cosmic microwave background, CMB radiation, the earliest known light in the universe. The CMB was emitted around 380,000 years after the Big Bang, once the universe had cooled enough for atoms to form. At that point, the universe became transparent, and this light has been traveling through space ever since. By studying the CMB, cosmologists can essentially take a baby picture of the universe. This ancient light offers clues about the universe's earliest moments and provides strong support for inflationary theory. One of the most significant breakthroughs came from the European Space Agency's Planck satellite, which captured detailed images of the CMB. These images revealed slight variations in temperature that matched the predictions made by inflationary models. This experimental confirmation bolsters the idea that inflation is not merely speculative, but a crucial element of our understanding of the universe's origins. Understanding the Big Bang, and what came before it, requires combining two of the most important theories in contemporary physics: Einstein's theory of general relativity and quantum mechanics. General relativity explains the large-scale structure of the universe, galaxies, stars, and planets, while quantum mechanics explains the behavior of particles at the smallest scales. To answer the deepest questions in cosmology, such as what space and time truly are, and where the universe came from, scientists need a theory that merges these two frameworks. Such a theory would allow us to understand not only the Big Bang, but also the conditions that led up to it. One of the most surprising aspects of the universe is its size. The farthest objects we can see are about 47 billion light-years away, meaning the observable universe is roughly 94 billion light-years across. This may seem strange, considering the universe is only 13.8 billion years old. How can we see farther than light could travel in that time? The answer lies in the fact that the universe has expanded over time. As space itself grows, the distances between objects also grow, making them appear farther away than the light travel time would suggest. Most scientists believe that the universe extends far beyond what we can observe. In fact, many cosmologists consider the universe to be infinite. The observable universe is simply the range within which light has had time to reach us since the Big Bang. There may be vast portions of the universe we will never see. This raises the philosophical question: is there anything beyond the universe? Most scientists don't think this question has a physical meaning. If the universe is infinite, there is no beyond. It simply continues forever. Even if the universe is finite, space and time themselves are properties of the universe, so it may not make sense to speak of anything outside of it. Just as the beginning of the universe is a topic of intense study, so too is its eventual fate. The best current estimate is that the universe will continue to expand forever, due to a mysterious force known as dark energy, which is responsible for the accelerated expansion of the universe. Before dark energy was discovered, scientists believed that the universe's expansion might eventually slow down due to the gravitational pull of matter. Some even theorized a possible Big Crunch, where the universe could stop expanding and collapse back in on itself. However, dark energy appears to be pushing galaxies apart more and more quickly. If this acceleration continues, the universe will keep expanding forever. Eventually, galaxies will drift so far apart that they become isolated from one another. Stars will burn out, galaxies will separate, and all matter will eventually decay. This scenario is sometimes called the heat death or freeze death of the universe. The story of the universe is the universe. From the beginning to the potential end, it is one of the most profound and complex stories in science. While we have gained significant understanding of inflation, which marks the beginning of the universe, many questions remain unanswered. What triggered inflation? What stopped it, and why? What lies beyond the observable universe? If there is a multiverse, how many other universes are there? As scientists continue to investigate the universe with advanced theories and technology, combining quantum mechanics with general relativity, we will undoubtedly learn more about these mysteries. The search to understand the universe is ongoing, and each discovery brings us closer to a response to the ultimate question of our existence. Looking into the beginnings and structure of the universe is not only a scientific endeavor, but also raises questions of existence, philosophy, reality, and our place in the cosmos. One of the key areas in cosmology is understanding dark matter, which is thought to make up about 27% of the universe's mass energy content. Unlike normal matter, dark matter neither emits, reflects, nor absorbs light, making it invisible. detectable only through its gravitational effects on visible matter. Gaining knowledge of dark matter is crucial for explaining the formation and dynamics of galaxies. Recent experiments and observations have revealed more about the properties of dark matter, but its exact nature remains elusive. Various candidates have been proposed, including massive weakly interacting particles, WIMPs, and axions, but no direct evidence of dark matter particles has yet been discovered. Through a combination of ground-based experiments, sky observations, and simulations, modeling how dark matter influences the universe's structure, the search continues. Another crucial area of research is dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy makes up about 68% of the universe's total mass energy content. Its discovery was unexpected, and has led to numerous theories, including the cosmological constant and dynamic fields like quintessence. Understanding dark energy is essential because it will determine the universe's ultimate fate. Scientists are studying how dark energy affects cosmic structures and whether it remains constant over time or evolves alongside dark matter. The study of dark energy and cosmic structure formation also provides valuable insights into the history of the universe. Observations of the cosmic web, vast clusters of galaxies in a network of filaments, show how matter clumped together under the influence of gravity, leading to the complex structures we see today. Supercomputer simulations aid scientists in understanding how these structures formed and evolved over billions of years. Cosmology and astrobiology intersect as researchers investigate the conditions that make life possible beyond Earth. The search for exoplanets, planets orbiting stars outside our solar system, has accelerated, with thousands discovered in recent years. Some of these stars host planets in habitable zones, where liquid water could exist. By studying these distant worlds, scientists hope to learn more about the potential for life elsewhere in the universe, and what it might look like. The significance of fundamental physics in cosmology is also essential. The search for a unified theory combining general relativity and quantum mechanics continues to challenge physicists. Theories like string theory and loop quantum gravity offer potential explanations for phenomena such as black holes and the early universe. As technology advances, our ability to observe and interpret cosmic phenomena improves. Space telescopes like the James Webb Space Telescope are revolutionizing our understanding of the universe, providing unprecedented data about distant galaxies and cosmic events. With each new discovery, we are gradually piecing together the puzzle of the universe's creation, evolution, and ultimate fate. The study of the universe is a rich blend of scientific inquiry and philosophical investigation. From the fundamental forces that shape cosmic structures to our search for extraterrestrial life, our knowledge reflects humanity's deep curiosity about the cosmos. As we work to answer these profound questions, we not only gain new insights, but also develop a deeper appreciation for the vastness and complexity of the universe. The relationship between observation and theory is crucial in cosmology. Innovations in technology, such as advanced detectors and machine learning algorithms, are improving our ability to analyze astronomical data. These tools help researchers sift through vast amounts of information and identify patterns that could reveal new insights into cosmic phenomena. Crucial field of research is gravitational waves, ripples in spacetime caused by catastrophic events like colliding black holes or neutron stars. The detection of these waves has opened a new window for observing the universe. By studying gravitational waves, scientists gain insight into the nature of these extreme events and can test gravitational theories in ways traditional methods cannot. The concept of cosmic time is also intriguing. Unlike our everyday perception of time as linear and uniform, cosmic time is shaped by the universe's expansion. This raises questions about the very nature of time itself. Is it an absolute concept, or does it depend on the observer's position and motion? These philosophical questions parallel scientific exploration, highlighting the multifaceted nature of cosmology. The study of the origin of the first stars and galaxies known as the cosmic dawn, is another critical area of focus. Understanding this epoch helps explain how the universe transitioned from a hot, dense state to the complex structures we observe today. Observations of high redshift galaxies provide clues about the processes that occurred during this pivotal time, supporting the creation of a cosmic timeline of evolution.